And what we're seeing here is a meter stick with a stack of 4 dominoes in this end and 4 dominoes in this end, balanced on a couple of dominoes in the middle. Okay. So you wouldn't expect 3 dominoes on that end to balance 4 dominoes in this end if they're balancing in the middle, right? You have 3 in that end, 4 in this end. Which way would it tip? Just point. If I had 3 dominoes in that end and 4 dominoes in this end, it would tip which way? Okay, it would tip toward this end. You're pointing to this end, right? That's obvious. I could take the dominoes off, but they'd probably fall or something, so I'm not going to do that. Okay. Now, if I wanted to move, well, if I wanted to replace this stack with another stack, okay, that's about 18 inches from the floor, okay? It's really more like 17. We'll just say it's 18 inches because that's a nice even number, visible by a lot of things. Okay. If I want to move it towards 9 inches from here, it's not going to balance anymore, right? If I move it here, what's going to happen when I let it go? Going to tip? Yes or no? Yes, no. Going to tip. It's going to tip this way or that way. Going to tip this way. Okay. And you know, most people understand that by the time they're 2 years old, playing with blocks and stuff, assuming they have things to play with. Okay. You know which way it's going to tip. But of course, at 2 years old, not a lot of kids know the mathematics. Okay. Matter of fact, coming to college, most people don't know the mathematics of it. Okay. So just intuitively, obviously I'm going to have to add dominoes over here to make it balance, right? Okay, so how many dominoes am I going to have to put there? How many more? Or if you wish, how many dominoes is it going to take here to balance the 4 dominoes here? And remember, I've moved it halfway to the fulcrum, right? So how many do you think? Show me. Okay, I see some responses. I see some uncertainty. So let me just get a handful of dominoes. Think I got enough? Is that going to be enough? How many think that's going to be too many? Okay, you're right. But we don't know until we do. Okay. So I'm going to take 2 of these. And I'm going to put 2 of them didn't do it. Think one more will do it? How many more do you think I'm going to need? 2 more. And that's what I got. So let's see if that works. Now, some dominoes are thicker than others. Fudge them just a little bit here to make sure I don't. Make sure I kind of use dominoes that average out to the same weight. That's what we have. Okay, that works. Okay. So what it is if I move this thing twice as close, I'm going to need twice as many. Right? So twice as close implies twice as many. Well, What if I moved it 3 times as close? Well, you might expect that it would take 3 times as many, and that's the case. Well, what we have here is a proportionality. So my question is, why is the number of dominoes required to balance the system and X is the distance from the fulcrum call it fulcrum, I'll say balancing point. Now I'm going to say fulcrum. Y proportional or inversely proportional to X. Okay, so we've got an answer. People aren't sure whether it's a direct or inverse proportionality. And since you haven't been taught to think in terms of proportionality, which is another huge deficiency of our system, you aren't, yeah, well, you simply aren't sure. Okay, but you know how to set up proportionality. So we can reduce this to y equals 4. That's 4 dominoes, right? Because y is the number of dominoes when X is 18, and X is the distance from the fulcrum, and that's 18 inches. Okay. So the proportionality expression, y equals what? Okay, we've got a good answer. Everybody thinks it's y equals kx, and that's correct. If the proportionality is direct, we're going to test it to see if we get the right answer. Okay. So y equals kx, y equals 4 when x equals 18. And then we want to be able to test that for different values of x to see what y needs to be. So go ahead and solve it. Okay, so y equals k times 9. All due respect, police dogs. Incidentally, on the trip here, there's a police car, lights on in the right lane. I got down a little close. It wasn't a big deal. We got through the light anyway, so it wasn't heavy traffic. Just, a few more cars than usual. But there's a whole line of cars just sitting there. Okay, couldn't see what it was as I was coming up on it. And as I passed, I looked over, and there are 3 police cars there. And then there's 2 vehicles, and somebody bumped somebody's bumper. Okay, they're pretty minor. Nobody's hurt. Everybody's standing around. A bunch of old people. I mean, a lot younger than I am, but they're old. Okay, so why are there 3 police cars there? How much backup do you need? Now, I'm not being critical of the police because you don't take chances. If people are available, you send them to the side of the accident, right? Or to whatever is going on, if there's nothing else going on. So it's perfectly reasonable, but it looks a little funny. Yeah. Everybody was okay. Everybody was visibly angry or injured, and the policeman was being polite. Good stuff, but it just little discrepancy. So what's a proportionality between the number of police cars that show up and the amount of need for police cars? Okay. So if there's not much need for police cars, you're going to have a lot of them. I mean, they might as well be there as anywhere. And on the other hand, if there's a lot of activity, you're probably going to only get one car, unless there's some aggravating factor. You know, they check the license and find out that this guy's just got out of prison for multiple murders. I don't think you get out of prison for multiple murders, but yeah, whatever. You know, they find that there's something dangerous about the person, then they're going to call for backup, and that's going to take priority, right? So there's all kinds of complexities to the way that goes. Anyhow, okay, so 4 equals K times 9, and K. And it's K times 18, not 9. K is 4 over 18, which is 2/9. So Y equals 2/9 of X. Now to solve the question, what is Y when X equals 9? Two nines of 9. And here's fuzzy on fractions, as almost everybody is. We're going to write that as 2/9 times 9 over 1, which is 18 over 9. There's a multiply numerators, multiply denominators, and that's 2. Well, if I put 2 dominoes there, this whole thing's going to crash. Okay, so direct proportionality didn't work. Now we could do a direct proportionality with the square of the distance, or the square root of the distance. Okay, that's not going to work so how do you? Because the point is, if it's a direct proportionality, if X gets bigger, whatever the power of X, Y is going to get bigger. Okay, unless it's a negative power, but any positive power of X, if X gets bigger, Y is going to get bigger. So direct proportionality is not the answer here. Try an inverse proportionality. Okay, people did well with this. We have Y equals A over X. Again, demonstrating that you remember what you did 2 days ago, which you had of a lot of classes. Okay, Y equals K over F. Not such a bad K, but I got it. Like something to be produced by alien civilization. Okay, Y equals K over X. And Y equals 4 X equals 18. So 4 equals K over 18. So K equals 4 times 18, which is 72. Now you just got done doing a multiplication, so it's real easy to then write, you know, Y equals K multiplied by X, because you got multiplication in your mind, you're picking up my habits. Okay, you don't want to do that. And you know, I am picking up everything on the board, but I really need to zoom this so it's a little more visible. I'll pause for a second. So you're going to rewrite your proportionality equation. Don't look at this, look at this, right? That's obvious, sort of thing I do all the time. So can't say you're in good company. Y equals 72 over X. So if X equals 9, Y equals 72 over 9, they. And that checked out because that's what it took. So we matched up our mathematics with the reality. Okay. Now, I don't know what kind of experiences you have. One of you lives on a farm. If you got something heavy and you got a big old iron bar and you want to move that heavy thing, what do? You rest that bar over fulcrum. Now, you want your hand to be closer to the fulcrum than the weight, or do you want the weight to be closer to the fulcrum than your hand? If you've ever done that sort of thing, you know that the closer the fulcrum is to the weight, the more leverage you have. Okay. So it's like if my fulcrum is here and I'm trying to move a heavy weight down here, I want to do this. Okay. Physics of that is as much work is going to get done here as here, but work is force times distance. Okay. So I move more distance here and I get more force down here. Force times distance has to be equal. You neglect things like friction, air resistance, and those things are pretty negligible in that case. That's another case of an inverse proportionality. The amount of force you get is inversely proportional to how close the lever is. Closer, more force. Less distance, more force. Same thing is going on here. It's exactly the same physics, but I'm not going to teach you physics. This is all just intuitive. But we are doing the mathematics because the mathematics is pretty accessible in this case. Okay, so the reasoning that could lead me to this is, well, first of all, a direct proportion say should be a direct proportion says, don't know how to talk either. Direct proportion says that Y increases with X. Okay. Now X is your distance. So if your distance increases, you're going to need fewer dominoes. Again, leverage. The further the dominoes are, the more leverage you have, and the more weight you can lift here. So if you got the same weight here, you're going to need fewer dominoes as you move out. And that's intuitively obvious if you think about it. Now, it's fairly natural to say, okay, let's try a direct proportion. I don't know what it is. Okay, it's an unfamiliar situation. And you set up a direct proportion and it predicts that you can balance this thing with two dominoes here. Okay. So here I'll say this is not so. I'm not able to read all that, but I say two dominoes at 9 inches doesn't balance. Then you think, okay, when you originally thought about this, I talked about twice as close. It takes twice as many, right? So if you have a measure of closeness, it would be a direct proportion with closeness. But it's not a direct proportion with distance because the distance is inversely proportional to the closeness. The less distance, the more closeness. Okay? And it's an inverse proportion. It's not an inverse proportion to the square or the cube or the square root. Okay? So the reasoning then is, if we focus on the fact that we're looking at distance, less distance means more dominoes. Once you get the idea that less means more, then you know that you're into some sort of an inverse proportionality. Okay. I mean, if it is a proportionality, not everything is a proportionality, but many, many things are. Many important things are. Okay. So anyhow, there it is. Now that we have this equation, how many dominoes will it take at 4 inches? Okay, well, I'm not sure I want to get that close. Okay, how many dominoes will it take at 12 inches? Okay, now you're working on it, but let me point out that you don't have to start all again from the beginning. You already know that if x equals 18, y equals 4, which leads you to this equation. So all you got to do is plug in your value of x. So now anywhere I want to go on this meter stick, I can do a very simple calculation and figure out how many dominoes I'm going to need. Well, everybody got that rather quickly. And I think before I even told you, just use this. I think you pretty much did that. Okay. But if I want to reduce that that stack to 5 dominoes, where should I put it? Okay, well, then 5 equals k over x. Okay. We're going to solve 5 equals k over x. Got to move over here. And knock the dominoes off. I got it right over here. Okay. Multiply both sides by your denominator. And you get x times 5 equals x times k over x. So that equals I've got the K there. So that five X equals K. Now I just used K, but K is 72, right? Oh, see what I'm worried about. So X equals K over 5. I think I've got a long piece of chalk here. You divide 72 by 5, you get 14.4. So that's around 14.5 inches. And approximate is okay here, because these dominoes aren't all the same. There's a little, this isn't exactly twice this, but it's close enough that it balances. So I move it over here to where it's about 14 inches away. Now here's 18 inches, and here's 4 inches. 4.5 inches would be about here. So I'm going to take these off. Oops. Okay. Take 3 of them off. And move these. So we're about 4.5 inches, and let's see what happens. I'm not sure if it helps them. Okay, there it is, right? Okay, so this whole thing works, and you understand that I could use this again and again if there was a situation where I needed to balance a certain weight. Okay, so it's like you got this thing, you need to keep it off the floor. How much weight do you put at what point on your lever to keep it there? I don't know it's necessarily a good idea to do that with a heavy weight, but there are other cases, but they're a little more subtle than this. As you know from last time, this is an equation of a straight line. Now what I want you to do is I want you to graph that straight line. By first finding y when x equals 0 and finding x when y equals 0. So find y when x equals 0, find x when y equals 0. That gives you 2 points on the line. See if you can identify what the 2 points would be, and then plot them on a graph and sketch the straight line that goes through those points. Okay, people are moving along well. I think we're going to get good plots on that. What we're going to do is estimate y if x equals -1.5, and estimate x if y equals 3. You could solve, and we're going to do that, but do an honest estimate based on your graph. and estimate, fractions or decimals, to the nearest tenth or something like that. And then we'll see what we actually get. Then we'll solve it and see how close you are. Okay, so everybody got it. Got a good graph, and you were able to solve the equation. Find y when x equals 0, you plug in x equals 0, and you immediately get y equals 5. Everybody did that, so I'm not going to write it out. So, okay, so we have here, and that corresponds to 0.05. Everybody got that, and you did a nice job of labeling it and showing it. Okay. Then find x when y equals 0. Well, you got to do a little work. You get 0 equals 2x plus 5. Subtract 5 from both sides, you get 2x equals -5. Divide by 2, you get x equals -5 halves. And everybody got that. Okay, this is your y-intercept. Your y-intercept occurs when x equals 0. Next, your x-intercept occurs when y equals 0. You want to keep that in mind because on almost every graph you look at, you're going to be finding x and y intercepts. And you have to know how to set them up. Then sometimes the algebra is easy, sometimes it's hard, and sometimes it's impossible. But that's what you do. There's a reasonably straight line. Okay. Now, -5 halves is -2.5. So I could divide this interval into 5 parts. Each part being a half. So there's 1. There's 2. Here would be 3. So -5 halves is between -2 and -3, halfway between. 5, of course, is up there where 5 is. So if I divide this into more or less equal intervals. Not very good. My 1 is too big there. So my estimates are going to be off, but they're always off, no matter how accurately you plot. So we have to think about how any flaws in the scaling of our graph are going to affect our results. Okay. Now we want to estimate y if x equals -1/2. Well, does x equal -1/2? Or 1.5. It's here. And I'm going to draw the whole plane line. And here's the graph point. Now here is a value of y when x equals -1.5. Looks to me like about 1.6. Okay. So the approximate coordinates negative 1.5, 1.6. Now we can test that. Made that without looking at the equation or calculating anything. Honest estimate. Closer than it should have been because my scale isn't that great, but I lucked out. Because if you plug in now 1.6 for X, what do you get? Well, 2 times 1.6 is 3.2. If you add 3.2, well, negative 3.2. Okay. Wait a minute. Yeah, sorry. 2 times negative 1.5. It wasn't that close. I put some numbers together and thought I'd lucked out. I didn't. Okay. X is negative 1.5. 2 times 1.5 is 3, so it's got negative 3 plus 5. Y should be 2. Okay. Well, I got 1.6 instead of 2. Not far off. 1.6 is kind of close to 2, but most of you had estimates closer to 2. So you probably estimated 2. Because you have pretty good looking graphs. Now, the bigger your graph, the easier it is to do a good estimate, and the more evenly you scale it. Okay. Well, there we have it. Now, we wanted to estimate X if Y equals 3. So where's Y equal to 3? I have a good color here. Okay, here's Y equals 1, 2, 3. Again, my graph is a little distorted. My 1 was a little too big, but here's the line. Y equals 3. Here's where the line hits my graph. And down here is my X coordinate. Okay. And it looks to me like X is about negative 0.8. So my estimate is 0.83. Negative 0.83. Okay, well, X is negative 0.8. What's 2X? It's negative 1.6. And negative 1.6 plus 5 is 3.4. So again, not a bad estimate, but probably distorted because I didn't divide my graph up quite as accurately as I could have. Okay. Okay, so here's my question now. What's the average rate of change of Y with respect to X? You can answer it based on the 2 points you know from the equation. Okay, well, some people got this and some people didn't. Since we did average rate of change, you want to reflect back on what you did and didn't learn by doing that assignment. And that's an ongoing process. What does it take to really understand an assignment? Now I keep advising you go back and work through some of the previous assignments if you haven't already done it without looking at your work or any of the videos. So if you really understand it. Or make notes that you can always reference, so you do that. Use a strategy that gets the stuff really into your head. Average rate of change Changing Y over changing X.
I am so sorry to interrupt. This is entirely my fault. I need to borrow Mr. Smith for just a second. Can I borrow him? It'll take a minute.
Let's pause. Okay, so the average rate of change is delta Y over delta X, change in Y divided by change in X. Okay. And the formula is great, Y2 minus Y1 over X2 minus X1. Okay. Don't use the formula without thinking what it means. Because if you use the formula without thinking what it means, everything goes right over your head. It's just a formula. You get the right answer and you go on with your life. Okay. And that's not how you learn mathematics. I mean, it's how you start. Formula is not a bad place to start, but I always start with the meaning, and that's the way we talked about it. Whether you picked up on that or not right now, make sure you understand that that's what it means. So what's the change in Y and what's the change in X between these points? Well, there's a triangle. If you look at this triangle, I'm going to draw the same triangle over here without putting it on the graph. But it's pretty obvious that this side of the triangle is 5. And this side is 5 halves. If you go from here to here, you move 5 halves of a unit. You go from here to here. And then from here to here, you go 5 units. Okay. The calculation is very straightforward. It's 2. And you just divide the rise by the run. And 5 halves, 5 is double 5 halves. Okay. That's the slope of the graph. But that's also Y2 minus Y1 over X2 minus X1. Okay. Or that's the rise. And that's also equal to delta Y. This is also a delta X. Or a Y2 minus Y1 over X2 minus X1. What's Y2 minus Y1 over X2 minus X1? Well, if this point's Y2 and this point's Y1, then Y2 minus Y1 is 5 minus 0. And X2 minus X1, X2, remember, here's our second point, here's our first. So X2, X of the second point is 0, and X of the first point is minus 5 halves. Same calculation. The slope represents the rate of change. Very quickly, since we've got less than a minute to go here. I'll just write this down, but I want you to start to digest. if the distance from, why is the distance from home in miles? X is the number of hours. And the slope is the number of miles divided by the number of hours between 2 points. That's between any 2 points on the graph. And it's your speed in miles per hour. Now, one of your assignments is slopes, applications of slopes. You see a lot of different ways that slopes can be applied, but it comes down to something as simple as 2 points on a graph. Find the rise, find the run, you got a slope, and that means something. Okay, if it's miles and hours, it means miles divided by hours because your rise is in miles, your run is in hours. And I want to take a quick look to make sure I see what you're. Okay, so today you're doing the equation of a straight line. And then on Monday, you have slopes, meaning of slopes, applications. And there's also one in between on multiplying and dividing and comparing fractions. Something you really want to tune into because again, people are usually pretty ill prepared on fractions. It's going to help you understand fractions better, even though you did pretty well. Okay, very good.